Hello from Ferl. Good morning to all participants in America. Good afternoon to everybody in Europe and Africa, and good evening to all in Asia and Australia. We have today a Bode Plot seminar to explain a little bit how to tune, optimize, and analyze a drive. My name is Daniel Viermann. I'm working since a bit more than 10 years in the motion support team, taking care of these questions of the motion products of backoff. During this webinar, we have the possibility, or you have the possibility, to ask your questions. Therefore, you can enter the questions in the chat room, and we will answer the questions later after this presentation. Maybe we do not have the time to answer all your questions, but we have your contact data, and for sure we will answer everything which is asked. For the beginning, I have here an overview about our TwinCAT measurement environment. This is a tool to do analyzation. For example, the TwinCAT scope view you are using more or less every day. Other tools like condition monitoring or machine learning analytics, and one part of the measurement is the Bode Plot tool. This is a frequency-based analyze tool to analyze servo drives and motors, and this is where we want to focus today. The agenda in detail. In the beginning, we have to check some basics, some basic knowledge about this. Then we go ahead, discuss the settings and requirements, what is needed to configure in TwinCAT to run this Bode Plot tool. Next step is the interpretation. When we have done a Bode Plot measurement, how to understand this curve, what figures are inside. And that it is not a theoretical session today. We have two parts in practical. Two mechanical setups are prepared, and we will measure and check these setups in detail. So that's what we want to do today. We are starting with an overview of a system. The question is, how is the system reacting? You can imagine, for example, a heating, cruise control, or a segway. This is an inverse pendulum. All these technical systems have a behavior. You have a command to this system, and you want to have a reaction. The best way, the reaction is exactly as the provided command. For your heating, it takes time, but it is nice when the heating is exactly reaching, for example, 22 degrees in the room and not more, not 25 and then 20, and then it takes time to get 22. So the system should react as the command says. So the question is how to analyze the system. How can this be done? And if the system is not reacting smoothly or nice, what options we have to improve, to tune the system, especially for electrical access. One option is to check this time-based, for example, with a step response. We have here on this slide 3 pictures. On the left side, there is a step response where you can see this is a nice behavior. The actual value is exactly on the set point value. The reaction is perfect, but in the middle you see another behavior. There is an oscillation. It is a stable oscillation, but there is an oscillation, and the reaction or the behavior of the system is not nice. On the very right side, there is another oscillation, and this is an unstable oscillation. The oscillation is getting higher and higher, and the system is out of control. So if it looks like on the left side, it's very nice. The other two possibilities are not that good, and we have to optimize them. And on a time-based system, that's not so easy. Therefore, the second way to do an analyzation and an optimization is to do it frequency-based. Frequency-based means we are checking this by a Bode plot. We are doing this here on this page step by step. On the left side, we have done this with a sine signal with a frequency of 1 Hertz. And you can see the set point is identical to the actual value is identical to the set point. If you check the ratio, it is 1, so behavior is nice. The second measurement was done with 5 Hertz. And you can see that the actual value, the blue curve, is a bit above the set point. So there's a small overshooting of approximately 20%. Acceptable, but not perfect as it is with 1 Hertz. Second frequency, the third frequency is 10 Hertz. And you can see the actual value is much higher than the set point. There's a factor of 2 in between, so the system is overshooting a lot. And with 20 Hertz, you have opposite behavior. That means the system is not reacting anymore, or only with 40%. So there is a derating or a damping. If you transfer these ratios, these time-based ratios, into the logarithm format, you can see in the table, if you have a ratio of 1 transferred to the logarithm format, it is 0 dB. 0 dB means we have a perfect behavior. The system is reacting as provided by the set point. There is a formula how you can calculate from the time-based to the logarithm-based format, and another interesting figure maybe is time-based. We have a factor of 2. That means in the logarithm format it is 6 dB. Maybe the question comes up now, why you're using a sine signal? I'm doing a motion profile, a point-to-point motion, maybe with a 7-phase profile, and I'm doing not a sine movement with my axis. The explanation is why we can analyze a system sine-based because of the Fourier transformation. This is shown in this slide. We will do that step by step that everybody can understand the background. On the left side, we have a sine period. We have another sine period with a higher frequency but less amplitude. And if we add both signals together, on the right side, you have the magenta curve. You see the addition of these two signals. And if we go ahead, we add a third sine period, a third sine signal with a higher frequency and less amplitude, and we add all three signals together. On the right side, you can see it's getting more and more like a rectangular shape. So if you have a velocity step to your electrical axis, this can be transferred by the Fourier transformation to sine periods with a very low frequency up to an infinite frequency. This is the explanation why you can analyze each system sine-based, because you can transfer each signal into different sine signals. Now we want to check some product things, some settings which are required. At first, the product name, TwinCAT Engineering 132X. That's the name of our TwinCAT Bode Plot product. What is required? Windows 7 or Windows 10. And you need a Visual Studio Shell environment, so an environment system of TwinCAT. On your target system, if you're running with a CX, for example, runtime is acceptable. The supported drives are listed below. You can do this with AX5000, with AX8000, with our servo terminal, and with the new products AMI and AMP8000. So these are the supported drives by this Bode Plot tool. It is for free, so there's no license required. It comes with a standard TwinCAT installation to your PC. These are the settings for TwinCAT or needed in TwinCAT. There is a dynamic container, or it is called dynamic container. This is required to have an oversampling available. If you run a cycle time with 2 or maybe 4 milliseconds in NC or CNC, this is not fast enough to have a good analyzation. We need the actual values of velocity much faster within each 62 microseconds. Therefore, we have realized the oversampling like in our oversampling terminals. Therefore, you have to add this container, and another TC-COM object is needed to prepare the set points. So 2 steps to configure, and then it's ready and you can use it. This slide shows some properties you have in the Bode Plot tool. I pointed out here the modes which are available, so you can do a frequency analyze, a Bode plot of our torque loop, of the velocity loop, and if needed from the position loop as well. The most interesting mode is the velocity Bode plot, because in this velocity loop you can see the behavior of the mechanics. The torque mode is not that interesting because it's based on the electrical behavior of the motor, and this is not changing. Therefore, normally you don't have to touch the torque loop, but the velocity loop is really interesting. And that's where we want to focus on today. We will start with a motor without load, so an empty motor shaft, to see how a Bode plot looks for an empty motor. Here's the curve, or in total there are 3 curves. We go through this picture step by step. The first graph shows the gain response. This is the ratio of the actual value divided by the set value. Maybe you remember the best is to have a ratio of 1 transferred to the logarithm format 0 dB. And as you can see, for example, for the magenta curve, the closed loop, this is the line starting on 0 dB. It means the motor is reacting perfectly up to maybe 30, 40 Hertz, and then this curve is dropping down. Then there is this blue curve. What's the difference to the magenta curve? I have increased the velocity gain factor, so the Kp is doubled. And therefore, the motor is reacting better. The closed loop is for longer time or for higher frequencies on the 0 dB line. So the motor is reacting better. And the black curve is again a doubled gain, and this is again an improved behavior. The same can be done for the integral part of the velocity loop, so the Tn. We are starting with a red curve. You see this red curve is going down earlier in comparison with the blue or with the green curve. The green curve maybe has higher overshooting, so the peak is reaching approximately 4 dB. So maybe this is a bit too much. You see on the right side, the Tn is only 2 milliseconds, so maybe a bit too aggressive. But the blue curve is a good compromise. There is no peaking in the blue curve, but yeah, the behavior is okay and better than within the red curve. You see the dashed line. The dashed line is the open loop. It's not measured, but it is calculated based on the closed loop. And you see as smaller the time, as higher the open loop is in the gain response. And this indicates that the motor, the system is reacting a bit faster. If there is a mismatch in the velocity, it is minimized faster, more quicker, or much quicker. but the negative effect, you can see the overshooting, the peaking is a bit higher. So in the conclusion is the blue curve here is an optimum. This is a very interesting slide and interesting topic. You have seen before the influence of the gain factor and of the Tn, but now the important question is, how can this curve be analyzed? What is the criterion? How can I say if this is stable or unstable? And we have two criterions for this, to do that, and I want to explain them to you. The first one is starting in the open loop gain. So the dashed line is reaching 0 dB. That's the orange arrow. We are going down into the phase response. Again, the open loop phase, and we're checking the distance to minus 180 degrees. That is called phase reserve. And this should be minimum 35 degrees, better a bit more. So this is the first criterion of stability. The second one is starting in the phase response. At high frequencies, the phase will reach minus 180 degrees. So that means the system is delayed, is a shift inside of 180 degrees. Then we go up into the gain response, and we are checking the open loop gain, the distance to 0 dB. That's called gain reserve. And the gain reserve should be 10 dB or more. And if both criterions are fine, you can say your axis is stable. Furthermore, there is a criterion or figure which indicates the quality of tuning of your system, and this is the bandwidth. The bandwidth is defined the closed loop gain crossing minus 3 dB, that's the dashed red line, or the phase at minus 90 degrees. In this case, minus 3 dB is reached at a bit more than 200 Hertz. So we have here in this picture a bandwidth of a bit more than 200 Hertz. That's again an overview. What we can do, we can measure the closed loop. So the system is always running as a closed loop. So we have actual speed and actual position, and this is used for the PI loop. But from this closed loop, we can calculate the open loop. I don't want to explain the formula in detail. I only want to point out that the measurement is done in the closed loop, and with the help of some mathematics, we can calculate the open loop. And both are needed to check the stability of an axis. Here are some filters, because filter will help us to optimize an axis. On the left side, you can see two filters, PT1, PT2, but the disadvantage of these two filters is a massive phase shift, 90 degrees or 180 degrees, and this is in practice not very useful. In practice, we are using the biquad filter in the middle or the notch filter on the right side. The notch filter, you can see there is a spike in the gain into the negative direction, and if you have in your measurement a spike in positive direction, you can add such a filter, combine both curves, and in the result you have a flat, nice looking curve. That's something we will do in practice later on with our demo unit. So the yellow marked filters are needed in practice. This is our first setup. We want to test the motor with a load on the motor shaft. At first, we have to add the dynamic container for the oversampling, that we're getting the values each 62 microseconds. We add the NC TC-COM object for the set point generation, and then we have to add Drive Manager project to scan the motor and configure the motor with some default values. When this is done, we have to enable the ADS port. Later on, we will do a time-based scope, and therefore we need this port. Then we can activate TwinCAT. We have enabled the access, and now we can add the Bode project to our solution and have the first Bode plot, the first measurement of our axis. The axis is running with default settings. What is needed? You have to select the correct PC, the target, the axis ID, and then there are some more properties. We have to choose the mode. We're checking the velocity loop. We define the start frequency, 1 Hertz makes sense, and the max frequency, 2 kilohertz. Number of steps, 100 maybe, then it's more detailed, our measurement. The amplitude, not that much, maybe 10, the same unit as the NC, and then we can start. Now we are starting with 1 Hertz, going up to 2 kilohertz. You can see we have a time-based signal. This is for information. And then we are building the ratio, output divided by input, transferred to the logarithm format. And you can see the bandwidth is not that high. We are crossing -3 dB early at a bit more than 10 Hertz. And on the right side, we have a massive peak. Now we are changing the gain factor. Maybe we double the gain factor. With Control Enter, I can download this, and then I run my measurement again. So we expect a higher bandwidth because the bandwidth is more or less proportional to the gain. You can see the bandwidth is maybe 20 Hertz, but we also will have a bit more problems on the right side at high frequency where we have this spike. The spike will be also a bit higher. And we have to do something because this spike is causing some sound, unstable behavior. The axis is not uncontrolled, but unstable. We add a filter, we add a result, and then we have the option to combine our measurement with a filter and simulate a filter to see which filter makes sense to eliminate this spike. Therefore, we have to choose the correct filter type. A notch filter makes sense. Then we have to find out the frequency. By the tooltip, you find it out, 1470 Hertz. We will enter this figure here. Define the bandwidth, maybe a bit less. And you can see the blue curve. This is the result, the expected result. There is no spike anymore. So we will go into the Drive Manager, activate such a filter in the AX5000. There are the same filters available as in the simulation. The notch filter was looking nice, 1470 Hertz and 750 for the bandwidth. You see on the right side the picture, so you see again how the filter works and looks. You can download. And when we have activated this filter, we can run the measurement again. And we want to verify the reality with our simulation. So we expect now the blue curve because that was simulated. Hopefully in practice it's the same. So until 100 Hertz looking identical, now it becomes interesting. And you can see in the phase and also in the gain that we are nearly identical with the simulation. Let's make an estimation for the gain. 25 kg/cm² is the inertia divided by the motor inertia. So we have a ratio of 17 multiplied with the default gain. So we expect a gain of 1.16 is possible. We try that. So massive increase of the gain factor. And then we start the measurement once again. You can make invisible the curves which are not needed anymore. Then it's a bit better to see. So you can see the closed loop is for higher frequency at 0 dB, which means the system is reacting perfectly. And at the same time, there is hopefully no spiking anymore, no peaking. That's the case. We can check maybe in detail some figures, the bandwidth and the peaking. The peaking here is a bit more than 1 dB. This is acceptable. And the bandwidth is around 80-85 Hertz. So a massive improvement in comparison with the default situation and no issue at higher frequencies. We see here in the next slide a comparison, time-based. On the left side, we have moved the axis with the default configuration, and you can see the oscillation. You see it in the torque, you see it in the velocity, and in the position error in the following distance. On the right side, we run the axis with the same profile, but after tuning with the improved or increased gain. We have activated the acceleration feed forward, and if you compare the position error, there is approximately a factor of 200 in between. So by the help of the Bode plot, we pointed out the problem. There was a problem, a resonance at 1470 Hertz. We used a notch filter to eliminate this, and in the end, this is the improvement you can see time-based. Here, once again, the comparison in the Bode plot view, the blue curve was default. You see in the closed loop a peaking at 8-9 Hertz. There's peaking of 6 dB approximately. So the system is overshooting. On the right side, you see the resonance frequency. And after tuning, we're getting the black curve, higher bandwidth, which is a quality criterium, and no resonances anymore. To understand this a bit better, we have prepared a second setup to do it once again. You see this mechanical system is a bit more complex or critical maybe. This is called a two-mass system. One mass is in the middle, a small connection to the motor, and the motor itself is also a mass. Therefore, we call it a two-mass system. Let's have a look. We add another Bode project for the AX8000. We do this with the AX8000 drive instead of AX5000. We have again to parameterize the Bode plot. So again, the target has to be selected and the correct axis, axis number 3. We define 100 steps. We have the amplitude, 10 is enough, 1 Hertz, and that's it. Then we can start our measurement. So with default settings, we want to check the system. You see again, closed loop starting at 0 dB, but then when it's going to higher frequencies, it's going down, reaching a minimum, and then it's coming up again. This is something where we have an anti-resonance here at 130 Hertz, and we have a resonance at 351, 52. This is typical for a two-mass system. We add again a filter to improve the situation. So we can use maybe another filter type. A biquad filter makes sense for such a mechanical system because we have to damp the resonance and increase a bit the anti-resonance. That can be realized with a biquad filter. You will see that step by step. You can edit the figures. We need to check it in the result that we see how our filter works. So we have to damp the resonance We enter the correct frequency, a bit more. And for the anti-resonance, we lift the curve, lift it up a bit, not too much, maybe like this. So the blue curve is much nicer. So we will transfer the filter settings into the AX8000 drive. In both drives, AX5, AX8, we have 4 filters available. What was it? 130. Correct damping factor. So the biquad filter is a combination of a low pass filter and a high pass filter. On the right side, you will see how the filter looks. For AX8000, you have to activate TwinCAT afterwards. When you have defined the filter to make it active, on AX5000 it was possible to download on the fly. When this is done, we enable the axis again, and then we will repeat our measurement to check if the reality fits with our simulation. When that's the case, the next step will be an increase of the gain. But at first we have to verify. So until 50, 60 Hertz, we expect no differences, but for higher frequencies, we want to get the blue curve. You can see small differences, but this is still acceptable and much nicer than before. We make invisible the first curves, so now we have the black curve. And here the same, we check the inertia. You see the load inertia, 2.5 kilograms centimeter squared divided by the motor inertia. Ratio of inertia approximately 18. Multiplied with the default gain. We are getting a result 0.11, which is maybe possible for the velocity loop gain. To have a rough estimation what is possible, what makes sense. Maybe we do it step by step, not within one step, but within 2 steps. So we increase the gain with a factor of 10. Now we start the measurement, and we expect a higher bandwidth because the gain is much higher now. You see the closed loop is still on the 0 dB line. Now it's going down, but we are in a range of maybe 80 Hertz. And at the same time, there is no resonance issue anymore. So, good improvement. Yeah, 80 Hertz, peaking 1 dB, both is nice, acceptable. Then we can maybe go ahead, increase the gain one more time, and do the next plot. You see also in the third curve, this time-based curve, the green and the orange actual speed, both are much nicer. The actual speed is much nicer because the bandwidth we are reaching is now higher. Now we check in the scope. So we are starting with our optimized axis, do a reversing sequence, and have a look how the axis behaves. You can see it's really nice behavior. There is no overshooting, no unstable behavior. And we go back here to the default gain, then we can compare it easily. You can see there is no vibration or oscillation in all curves. So it was really helpful to tune this axis, going back to our improved figure. And then The last step is the acceleration feed forward, maybe 100%. This is then minimizing the position error again. So these are the steps of optimization. I have here prepared another slide to compare it. On the left side, massive position error. On the right side, after tuning and with the feed forward, it's reduced a lot. So a factor of 70 approximately is in between. There is still a small vibration on the actual torque. That comes because the mechanics is not built perfectly. So there's a small unbalanced load. Here in the comparison in the Bode diagram, the brown curve shows the anti-resonance and the resonance. And after our tuning, the blue curve is without resonance and with a higher bandwidth, approximately 100 Hertz. So this was a second example, or in total we checked with 2 examples how you can optimize an axis, analyze an axis with the help of Bode Plot tool, and you can have a massive improvement. Okay, so the time is going on. Therefore, I want to say thanks for your attention, for joining this webinar. If there is still a question left and not answered, we will do that later because we have your contact. Yeah, thanks for joining this meeting. I wish you the best, a good day, and I say goodbye from Viermann.